The next speaker is going to be Paul Sathre and from Virginia Tech. And the title of the talk is Initial Experiences in Porting a GPU Graph Analysis Workload from CUDA cycle to CHIUW.
Okay, well, thank you for the intro. Let's see, is it coming? There we go. Thank you for the introduction. I'm Paul Sathre. I'm a research programmer in the Synergy Lab at Virginia Tech. And yeah, we tried porting a graph analysis workload that we have in both CUDA and SYCL to CHIUW because we're excited about the new GPU support. So I'm supported by a senior PhD at Sathre and our lab boss, Dr. Wu Feng. So we've done quite a bit of GPU computing over the years. I've personally worked with cosmologists and neutron physicists and a bunch of other ists supporting their goals of getting computations running on the GPU. And we've done a lot of that computation in the existing GPU languages, but we're always on the lookout for something that might be more productive. They all reluctantly were willing to learn a little C or C++ to get the GPU performance, but they would have preferred something higher level. So now that CHIUW has built-in GPU support, it's on our radar, and that's something we'd like to look into. So the first time you're looking at any sort of new programming model, you typically write a vector add, right? So that's what I did. I wrote one in CHIUW, and then I wrote a similar vector add in 3 languages that I've written before in my career as a GPU programmer. So the first thing I learned was OpenCL because I care about portability more than most other things. So it's very low level, it's C, and I spent 10 years writing that and tools around it. And you're not supposed to be able to read this. It's just a lot of overhead to do a vector add. But more recently, we've been writing SYCL in the context of FPGAs, but it also is portable to other GPUs. And it learned a lot of lessons from OpenCL. It's got lambdas and accessor semantics, and it leaves a lot of cool space in the spec for programmers and compilers and runtimes to do smart things. But it's still really verbose. And then finally, if you're talking about GPU computing, you can't really avoid the big green elephant in the room. And that's most kernels are written in CUDA if you don't need portability. And it's C++. It's less verbose than SYCL, but it's fundamentally still C++. But this is a CHIUW workshop. And hopefully that vector add is actually legible because CHIUW is more productive than any of these other approaches that I've been writing for the last decade. And it's also portable. You can run it on NVIDIA and AMD GPUs today, which is, it keeps that part of me happy. So all these languages have a way to write and invoke kernels. CHIUW is using array promotion here to do that. They've all got ways to allocate and free device memory, and they've all got ways to transfer stuff to and from the GPU. But the CHIUW is just so much more succinct. But anywho, that vector add's a regular application. So is Saxby or Triad. Like, we wanted to test it with something harder before we, completely dove in. So that's why we're looking at a graph analysis. We wanted to get a better firsthand understanding of the programmability as well as the actual GPU performance we'd get out of something that was more irregular compared to these existing languages that we've been writing for a while. So our workload is called edge-connected Jacquard similarity. Jacquard similarity is a very old metric. It's like 100 years old or something, but it's just the intersection over the union for 2 sets of stuff. But when we apply it to a graph, we do that for every single pair of vertices that are connected by an edge. So it's essentially a batch of order E set intersections, which means there's a lot of indirect access. And there's approaches in the literature to help with that, but this is GPU land. We can just oversubscribe a whole bunch of threads and use fast context switching to hide a lot of that too. So that's the way our code's written. It's not designed for CPU. It uses no ops and things like that to keep GPU threads behaving the way GPU threads should. And again, the reason we care about this application is really as a proxy for more complicated intersection algorithms, recommendation engines, community detection, or things like that. And to get a firsthand understanding of how good GPU CHIUW is at representing these. So our approach was to take our existing CUDA and SYCL application. We've written it in 2 languages, so now we've got a third. And inside of it, it's got 2 different pipelines. Sathre has written an embarrassingly parallel implementation. It assigns 1 edge to thread. So that's good if the workload's a little bit more balanced or sparser. And then we also port the old cuGraph implementation from Fender et al. 2017, which uses a 3D composition where one dimension is mapped to sources, one dimension is mapped to destinations, and another dimension collaborates over the intersection. So that one was fun to port. And it's a little bit better on denser graphs because you have to amortize those additional threads. So with that code ported, we reflected on how programmable we found the experience. And our goal was first to get it running on the GPU and make sure the performance was okay, and then start working backwards towards making it more CHIUW idiomatic, or I think the term Brad uses sometimes is CHIUW-tastic. But right now, it's definitely still CHIUW how a C programmer would write it, and we know that. So we're only using array promotion in one spot, but we have identified some spots to take better advantage of that. So that should help our line counts in the future. And we've also already identified a place where we can revisit how we're dealing with a generic disk format we're using that has 32-bit or 64-bit members. So the first thing I had to do in CHIUW was learn generics, which was fun. But anywho, even despite writing CHIUW like a C programmer, we had a considerable savings in terms of source lines. The kernels, we only saved about 15 lines, but the whole program, as we've seen in some of the previous talks today, saved, I think, about 450 lines. And I do think we can golf that down. But it wasn't all sunshine and cupcakes. Porting that 3D vertex-centric code was more complicated. When we submitted this talk, it actually wasn't working on the GPU yet, but with some help from Engin and Andy at HPE, we got it working. So it didn't initially GPUize. The way we were trying to do the 3D decomposition, it didn't want to run that on the GPU. So we ended up linearizing it and then logically creating a 3D index space. That wasn't too bad to do. But we also had a bunch of 4-by loops. That's a pretty common pattern in GPU code because we want to keep threads aligned to memory accesses. So we just advance by the thread count instead of by one. And the way the by clause is implemented, that also doesn't GPUize yet. But you can replace those with while counts. It's not a big deal. But then finally, because there's collaboration in the intersection kernel, we did need an atomic accumulator, and CHIUW's atomics don't run on the GPU yet. But Andy pointed us to a quick way to do an extern call from inside the kernel, and that got us finally running on the GPU. But throughout this process, one of the things that as a developer I found really nice was that CHIUW just mapped this loop to the CPU. So we were still able to validate the upstream and downstream kernels for correctness. It just ran a little bit slower because it's GPU code running on a CPU. But it worked, and that was super cool. So with that, now that we've got the code, it's working. They both run on the GPU. We had to test how it performed. So we used an existing data set from our previous FPGA work. I'm not going to read everything on the slide, but it's all open source. You can get it at the links on the bottom. But the important things to note are that we go up to a couple 100 million vertices, 500 million edges, and we've got densities from anywhere from 2 to about 160 neighbors. But they're not all easy graphs. We've got some that are really severe. Our most connected vertex has almost 1.3 million neighbors. So some of them are a little bit nasty, but they all fit within the GPU. We're going to address scalability to multiple nodes or multiple locales later. So in terms of that CPU performance, when we didn't quite have the vertex-centric code running on the GPU yet, it's a great feature for validation, but a GPU-optimized loop running on the CPU, you shouldn't expect it to be efficient. No-op threads don't make sense in a CPU context in the way they do in a GPU context. But again, it was great that we were able to transparently map that for-all to the CPU while we were still working to get it on the GPU. But if we remove these CPU slowdowns, then GPU CHIUW starts to look pretty good. Our minimum performance was about half as fast as the original CUDA, and our maximum performance was actually almost twice as fast as CUDA, which was completely unexpected, but a pleasant surprise. But in summary, there's definitely some room for tuning on the sparse end. That could be in our code, it could be in CHIUW's code. These results are too hot off the presses to know that yet, but we'll look into it for future work. But as you get to denser graphs, you really start seeing performance parity, which was way better than we could have expected when considering a new GPU language. And then there's a couple cases where CHIUW outperforms CUDA, and we certainly want to figure out why that's happening and feed those insights back into the CUDA and SYCL implementations. So with that, I'll start wrapping up. In terms of future work, obviously there's some performance gaps and gains to understand. We already know some ways to make this more Chapel idiomatic now that we've got a couple extra months under our belt. And we do, now that we have seen some really promising early results, we want to bring over some optimizations from previous work and other approaches in the literature. And as a relatively new Chapel developer, I've got a short wish list there. I do miss Clang format. And when I use Nsight Compute, I would like to be able to name my kernels, but those are minor gripes. I'm really, really happy with Chapel so far. So in conclusion, we're always on the lookout for more programmable GPU languages. As much as I like having a job, there's more data scientists than I could possibly help. So having languages that are accessible to them is great, and Chapel is looking pretty good so far. It was pretty easy to port to with a C on GPU's background, and we ended up with a code that was, the kernels were a little bit less verbose than CUDA, but the whole program was substantially less verbose. And I think we can get that down farther now that we have a better understanding of how to write stuff in Chapel. And then the real reason we're here is to make sure the performance keeps up, and it's within a shout. Between half and 2 times the performance of CUDA with a geometric mean of about 87% is a really, really good start for irregular algorithms that are not easy to get running efficiently. So if a data scientist asked me today what for a GPU language that wasn't C++ or C based, there's a good chance I'd point him this way, because it really was not bad to write at all. So with that, I need to acknowledge we are funded by the NSF Center for Space, High Performance, and Resilient Computing. And you can get our Chapel code and the data sets today on GitHub. So with that, thanks for your attention. I'd be happy to take a couple questions if we've got some.
Thank you very much. First question is from Dan, who has his hand up.
Oh, sorry, that was a clapping hand.
Oh, sorry. Okay.
That's okay, I appreciate it.
Okay, Paul, can I ask you to please stop sharing your screen while we get into the Q&A so that Engin can start sharing his. And I think we do have a question from Brad.
Okay.
Yeah, thanks. I haven't typed it in. It's kind of a high level question, but I was intrigued by the fact that well, first of all, I want to say that was a great talk. I really enjoyed it, especially not having heard you talk before. Given that you mentioned your experience with targeting FPGAs, I was curious about 2 things. One was, well, maybe it's the same question. Do you think there is a future in which Chapel would be an FPGA targeting programming language? Do you see a path there, or do you think it's too big of a stretch given the sort of very different nature of FPGAs in terms of being spatial programming rather than kind of temporal programming?
So that's a very good question. I have about total maybe a year to a year and a half of FPGA experience. I've only ever written it from an OpenCL or SYCL level. I've never done RTL. And those approaches have worked, but there is some resistance. It's really hard to say. I like the abstraction, but it's far enough outside my expertise that I can't comment too much more on it.
Okay, thanks. I appreciate you considering it. And yeah, I don't come across people who both use FPGAs and use Chapel very often. And so that's where the question came from. So
I'll be honest, I'm happy to be back on GPUs.
Fair enough. All right, thank you.
Thank you very much. That's perfect timing.